Never saw Jesse again.
This is the most unusual introduction I've ever had.
Everything okay, Jesse?
Everything, I just want to make sure that there's kids out there. Right?
Okay, yeah, I went and clapped, so.
I'm still hearing voices. Hey, good morning, everyone, and welcome now to week 2 of TASI. So hopefully you're all rested and refreshed after your weekend adventures. And we're going to be starting things off this morning with Lloyd Knox from UC Davis, who's going to be telling you about the invisible universe, LambdaCDM, and beyond. So Lloyd, please take it away.
Thanks, Jesse.
Is the mic on, Lloyd?
Yeah, can you hear me okay in the back with this? Yeah, okay, thanks. So this is my second time at TASI. The first time was only 31 years ago. It was 1993, and which I guess you could have figured out. And the SSC, the Superconducting Super Collider, had just been killed. I remember all of us writing letters to Congress trying to change that. And now it's 2024, and the NSF has, like a month ago, told us that we can't have CMB S4 at the pole. I don't know if you've heard this news, and maybe we'll be able to turn that around. But maybe I shouldn't come to TASI again. Although it's probably not my fault. So my goal for the week is to improve your ability to think about departures from LambdaCDM and how signals in light element abundances, CMB temperature, and polarization anisotropies, BAO data, and supernovae data are affected by how they get constrained in the how they can constrain the LambdaCDM model, and also how they can constrain departures from the LambdaCDM model, and perhaps vice versa too, right? So we get the data, and can we, how do we go from what the data look like to positing what could be the underlying physical models that could explain the data. So, and today, I'm really just going to go through, and to try to get us all on the same page. Today, is this far enough that you can see this, Ethan?
That's a good sign.
Okay.
It's a good font size, too.
Okay, thanks. All right. So today, we're just really working on defining LambdaCDM, actually. And that'll, bring up some of the physics in the process of defining it. I think that's all we're going to manage to do today. And tomorrow, we'll get into the phenomenology. And if there are particular things you want to hear about in the rest of the week, let me know. So there's an advantage that I don't have my lectures all written yet. So just before getting into defining LambdaCDM, just a little bit of personal history. In 1990, I was looking at where to go to graduate school, and I ended up choosing go to University of Chicago because I found out about what was happening there at the time, and more generally what was going to be happening in the field of cosmology over the next few years. And the other thing I was thinking about was particle physics, and the comparison of the two fields really left me with this sense that the particle physicists were kind of, they had this very standard model and successful, and then they were they were a bit stuck. And whereas cosmology, we didn't have anywhere near a robust history of a model that had been so well tested with data, but we did have big questions, and we knew that there was a data coming that was going to allow us to have to find out a lot, and that's all been true, but really from like 1995 to 2003, we saw the establishment of a standard model in cosmology, and here we are, 21 years later after that 2003, and we still have the same standard model of cosmology. A lot of the big questions we have are still the same, right? What is the dark energy? What is the dark matter? Why is there an excess of baryons over antibaryons? How did that happen? What is the generator of the primordial fluctuations, right? And how is that all related to the rest of physics? So let me just tell you about LambdaCDM in a nutshell. I want to get us all on the same page. I don't know, and I've had to guess about where you all are, and I'm imagining it's fairly diverse in terms of what you all know already. Just one brief thing about the success of LambdaCDM. In 2009, I was thinking about what we're going to learn from the South Pole telescope, measurements from the South Pole telescope, and if I plot the CMB power spectrum here, we had these great measurements from WMAP, tracing out like the first three peaks in this power spectrum. So tight data, constraining this, and then not much past here. But we could take the WMAP data and use it to constrain the cosmological parameters of the LambdaCDM model and make a prediction for what we should see out here. And the 68% confidence region of that prediction was about as thick as this line of chalk here, right? So this is an incredibly precise prediction. And so I realized, we're going to be making precise measurements here with South Pole telescope and with Planck. And so we're definitely going to see a failure of LambdaCDM. This is going to be great. But what happened was the data points basically fell right on this curve, both from SPT and Planck. And the story of cosmology since 2003 and even earlier has been, the one take-home line has been, standard model performs according to expectations, right? Standard model is triumphant. So it's worth, understanding what this model is and what gets us there, and since we're interested in discovering new physics, right? How will new physics show up and influence observables? So let me get into exactly what LambdaCDM is, because it sounds deceptively simple. Okay, you've got lambda and you've got CDM, but there's a lot going on in it. So LambdaCDM, in a nutshell, maybe two nutshells. So first we've got an expanding space-time governed by GR. And at early times, we have these properties. That it's gently perturbed from homogeneity and isotropy, and flat, right? So the mean curvature equals 0. It's gently perturbed away from homogeneous, isotropic, and flat. And what are those perturbations? I'll say more. Let me just. I'll say more about the perturbations later. Right. So let me just leave it at that. We have all the particles and fields of the standard model of particle physics. We have a thermal background of photons. That today have a temperature of about 2.73 degrees Kelvin. In fact, this is essentially serves as how we define what today is, right? You take a model. How do you know? Your model has all times in it. How do you know what is today? Well, where in your model is the temperature equal to 2.73 degrees Kelvin? This is probably measured more than anything else we have to pin down what we mean by the current epoch. So that's useful in that regard. And the chemical potential of this photon background is 0. We have a small but positive baryon to photon ratio. This is about 6 times 10 to the minus 10. Oh, right. Oh, no, this does go up. A similarly small lepton to photon ratio. This is not probed anywhere near as well, but this is an assumption in there is that this is effectively 0. And if we take all of these three things together, then we also have at sufficiently early times a plasma with thermal distributions of all particles and antiparticles. So even neutrinos, sorry, am I getting too small here? Or is this okay for your young eyes? Okay, good. So even for neutrinos, at early enough times, reaction rates are fast enough that thermal distributions will be generated. So there's all this stuff in the plasma that just flows from some basic assumptions that we have, that we have this thermal background of photons. We have, the small excess of baryons over antibaryons. Similarly with leptons, and from that we get this rich primordial soup. Of course, there's two more ingredients in the LambdaCDM model. We've got lambda and CDM. And this you can think of, as you probably know, as energy associated with every cubic centimeter of space. And the cold dark matter is, in the LambdaCDM model, there are many different particle physics models of things that can be CDM, but in just thinking phenomenologically in the LambdaCDM model, CDM is non-relativistic particles that only interact gravitationally. And that have a, they're non-relativistic, so they have a very small velocity dispersion. That's the cold part. The dark is they only have gravitational interactions. And the matter is non-relativistic. And to say a bit more about the perturbations, they are initially adiabatic. So, okay, I really don't like it when I'm the only one talking, so I'm going to stop here and just ask someone to tell us what adiabatic means here in this context. Because I'm sure some of you know. Or if you don't know, that'd be really helpful to me to know. Yeah?
The process occurs slow enough that the entropy change is negligible and it's therefore reversible.
Excellent. So that is a very, generally that's what we mean by AD. Oh, the process occurs slow enough that it's reversible, and so it's slow enough that there isn't entropy being created, and it's reversible. And yeah, so that's generally true. In this context, though, it's saying something about the can you convert that to the nature of perturbations, or does somebody else have an answer that relates to the nature of these perturbations more directly? Yeah.
So potential perturbations are very small.
So it doesn't have to do with the amplitude, but thank you for giving that. Yeah.
The perturbations of different species kind of evolve together, like in sync.
Right. Okay. So one way this is often stated is that if you have, so this is similar to what you were saying, if you have some fluctuation and at some position x, then yeah, at some given time t, then you're going to have at that same location and time in some other species y, that these are equal. So these fluctuations in different species are going to trace each other. Now what is this? Another way of stating it, though, which this is one of the ways I wanted to bring up, it's stated, but another way of stating it that I like, and which goes like this, that I'll write out here. The local state of matter e.g., what's the ratio of nx over ny at x and t, is the same as in the background universe. So we do this split, right, between, there's some arbitrariness to the split, but in evolving a universe that's slightly perturbed away from homogeneous and isotropic, we choose, okay, this is the background, and then that defines the perturbations away from that background, the mean. So local state of matter is the same as in the background at some slightly different time. T plus delta t of x. So note that this then follows from this, because if, this is saying that nx over ny is not departing from what it is in the background. So we have delta of nx over ny equals 0. There's no change in that. And that directly implies this, right? If you just expand that. I like the statement of it, too, because it also makes it clear that this is what we expect from the simplest models of inflation, where the difference of these homogeneities you can think of as arising, well, inflation ended earlier here than it ended over here. And so the difference between these two places, is just how much expansion has, at some later time, is how much expansion has happened in this region relative to this region, so that then leads to this picture. Yeah.
Since we are talking about perturbations, I also have heard the isocurvature perturbation, but I don't know the definition. So
right. So. Oh yeah. Thank you for the reminders and repeating the question. The question is or a comment is I've heard about there's also things called isocurvature perturbations. Could you tell us what those are? So in isocurvature perturbations, instead of everything tracing each other, you'll have things compensating each other. So you could have there's many ways to set up isocurvature perturbations. One way would be where you have an excess of dark matter, you have a deficit of radiation, so that as far as their contribution to the curvature, they cancel out. Yeah, thanks.
Lloyd, I'm going to recommend, since this board doesn't move, that you not go.
Let's stop there. Okay,
just
thanks.
Start on another board.
Okay. So there's one other thing about the perturbations I want to mention now, is that they are statistically homogeneous, isotropic, Gaussian random field. And I remember being a student and it being really hard to actually find out the definition of this. Well, I didn't have Google then. So anyway, I will expand on this a bit later, on what exactly we mean by that something being a statistically homogeneous and isotropic Gaussian random field. Okay, so that's the LambdaCDM in a nutshell. And I want to go on to talk about some key parameters in the model and define them. And then before I talk about key epochs in this picture of the cosmos. So yeah, maybe I'll just start here. So key parameters. So one is the temperature of photons today. As I've said, this is tightly constrained by measurements, mostly by measurements by the FIRAS instrument on the COBE satellite. And I didn't actually put into my notes what the actual measurement is, but it's sub% precision on the temperature. And it makes sense to just talk about the temperature because also we see no evidence of any departure from a black body spectrum, right? So T gamma 0, again, with a chemical potential that's 0. The baryon to photon ratio is another key parameter, and it can also be expressed as the baryon density today, because from this we know that the number density of photons today is basically pinned down for most of our purposes. So we can talk, instead of talking about the baryon to photon ratio, we can just talk about the mass density in baryons. And that's often how we express this. Another key parameter you may have heard something about is the Hubble constant. And so this is, of course, how rapidly space is expanding today in kilometers per second per megaparsec. You can think about, right, and at least in terms of a uniform universe, then we have an expansion happening so that there's around 70 new kilometers created in a given megaparsec each second. Right, so that's how we can think about this expansion of space. We have h equals a dot over a as definition of the Hubble parameter. The naught means today. What is a? This is the scale factor. And at least for the background, we have this relationship. With k equals 0, that's the mean Thank you. Thank you for catching that so quickly. I really hate that. I always do stuff like that, and then 2 minutes later, no one's heard anything I've said because they're like trying to parse. So anyway, I encourage you, even if you're not sure if I made a mistake, please ask me if I did, if you think I might have. And then we also have this important relationship, which follows from the time-time component of the Einstein equations in this isotropic and homogeneous spacetime. Where this is the total density, including the density in the cosmological constant. Again, in the standard model, k is 0, but let me just put it there for generality. Oh, thank you.
So did you say what mu is?
Yeah, so mu is the chemical potential. One way to think about the chemical potential is like temperature, it's a parameter that tells you about the phase space distribution, the momentum space distribution of the particles. And so let me just be explicit about that. For bosons, the Bose-Einstein distribution and then since it's bosons, we can remember the bosons are the ones that have a condensate. They get the -1, right? And fermions get the +1. So one way of thinking about the chemical potential is like temperature, it's a parameter in this distribution, defining what the momentum distribution is. And then if you integrate over all momenta, it's telling you about the number density of particles, right? So it's also the number density is affected by the value of the chemical potential. Anyway, that's one way of thinking about what the chemical potential is. Let me just, since I'm listing the parameters out here, let me just add k = 0 here. And now we often use these parameters, x and omega x, that are, when talking with people, is inconveniently the same letter, as said, right? Capital omega and lowercase omega. And let me, so these are defined usually according to the Friedmann equation today. So this expression serves to define what we mean by the critical density today. So this is true even if k is not equal to 0. And so that by definition, right, this is, I could have just written critical density today is 3h naught squared over 8 pi g. That's the definition of the critical density. It's just telling you about the expansion rate. It's the expansion rate and density relation you have if k is 0. And then we define rho x comma 0 over rho c comma 0. This is usually what people mean when they just write omega matter, say, omega sub m. They mean today. But it's also true that sometimes, without saying so, omega x equals rho x over rho c, right? And it's time dependent. And it's usually really clear by context, as long as you know that there is this difference. Right. And then the lowercase omega is omega x h squared, where h naught equals 100 little h kilometers per sec per megaparsec. This is convenient because, living in here is this 1 over, is an h squared, little h squared. And if we just multiply, if we get rid of that by multiplying by h squared, then this is just about the density. It has nothing to do with the expansion. It's the physical density of species X in just strange units, but it's the physical density, as opposed to a ratio with some other density. Right. And there's two parameters governing the spectrum of perturbations, AS and NS, where one way of defining these is as the power spectrum of curvature perturbations, and I'll say something more about power spectra later. So there's a parameter that controls the amplitude of this on pivot scale 1, and NS is this spectral tilt. Where K is, right, we're always thinking about the perturbations one Fourier mode at a time, because those are the things that evolve very simply. The Fourier modes are eigenmodes of the Laplacian operator, so they really simplify the partial differential equations. And therefore the dynamics are simplest when you're thinking about a single Fourier mode at a time. So the K here is the co-moving wave number of a given Fourier mode, right, where lambda equals the wavelength of the perturbation is 2 pi over K. At least this is true, I should say, at early times. And so there is this pivot scale introduced. That's necessary to define AS. And you, yes?
Yeah, so are we assuming that this is produced in the inflation? Or
This is after inflation. So LambdaCDM, I mean, there's no like Academy Française that's dictating what the LambdaCDM model is, right? So there are variations in what people say it is. And I think almost no one includes inflation as part of the LambdaCDM model, right? So it's I would say and most people would say it's our best guess at what generates these perturbations that are part of the LambdaCDM model. This is so this could be just in the radiation dominated era, while the wavelengths are much larger than the past horizon at the time. I should have repeated the question, although now I've forgotten it. Oh, is this during inflation or?
yeah, but I guess you were saying that's before recombination.
It's before recombination. Oh no, you're scratching your head. So it's. Maybe I should. So it's at early enough times that the perturbations that we're interested in, the expansion timescale and the age of the universe is much smaller than the dynamical timescale. So you don't have on wavelengths this large on those timescales, there's no time for pressure gradients to cause transport. So this is back in an early time when these fluctuations are kind of frozen, right? They're not evolving yet. They're waiting until there's enough time to move stuff around. Yeah.
Is that power spectrum dimensionless or dimensional?
This is actually dimensionless. So this is a dimensionless number, and so which. So actually, well, I don't use, anyway, I actually, so in full disclosure, while defining AS and NS this morning and, making sure that I knew one time my lecture started, I wrote this down, and then I was also concerned, there are dimensional concerns that I had here, and this, and So that I did not sort out. So let me get back to you about that, because this is a little weird.
Yeah, I think just in the literature it's common to define like KQ.
That's exactly what would, to my mind, would make this, that would then make this dimensionless, right? You know, because there's, yeah. So sorry. This is, you know, written down this way. I went to the Planck parameter papers, of which I'm a co-author, so I'm not blaming others, and this is written down there. Okay, so what you're asking about later, anyway, we'll come back to this. I'll get this sorted out. Thank you. Yeah, yeah. Sorry? Row C. This defines row C today. And you know, if I just remove the zeros, it would define it at all times. And we call it the critical density. And it's this density that, you know, for a given expansion rate, if you have that density, there's no curvature, right? So if you put in, if you set rho equal to rho C, then you'll find that k equals 0. So why what?
Why the bracket? Why is it still true even if k is not 0?
No. This is still this. Well,
I think the question is, tells you something about when k equals 0, then why is it still the same definition even if k is not equal 0?
Thank you. So I'm not going to repeat the question because I think just my answer will clarify it. This is so this is true regardless of whether k equals 0. So now let's assume now let's say if rho equals rho C, and this defines rho. Yeah. Okay. But let me just, so I won't go through the algebra then, which is pretty simple. Everybody could go through it. I'm saying now, if you take this equation, which is also true whether k is 0 or not, you know, with the assumptions we have, and you insist that the density is the critical density, then because of this definition, you know, you'll find k is 0. Right? Okay. Yes. All right. Yeah. Yes, you. Just h. And we have an h squared here because the critical density, right, has an h squared. And let's see, on the end there first.
So this is maybe a slightly sillier pedantic question, but what do you mean by photon number density? Like, isn't this formally infinite if I have a plane wave or something?
So here I'm talking about, maybe I should have put a mean on this.
Can you repeat that question?
Yes. What do you mean by photon number density? And then there's something like, isn't it infinite if I have a plane wave perturbation? Did I get that right?
Yeah, like if I have a classical wave, I don't generally have like a number state of photons or something.
Ah, okay. Well, we're in a limit with the photons generally throughout this history, where a description in terms of we don't think about through the full quantum mechanics, and we're in a regime where it makes sense to be thinking about individual particles, right? So we're talking about number densities of photons, and implicit here was a mean. So I'm not talking about perturbations here, right? So I'm talking about the background value of that. Yeah. That's a key parameter. And then there are other questions. Yes.
So I've seen KP is always like a fix of 0.05.
Could you speak up a little bit, please?
Oh, sorry. I just wanted to say, so if I redefine KP, the pivot scale, then
Yeah.
I can redefine NS and AS and have like my macron spectrum. Is that like a correct statement?
So yeah. So the comment was if you can if you change the value of KP, then you change the value of AS and NS, and it would be the same thing.
So the question is, I know the current pivot scale is something it's kind of standardized. Is that random, or is there a reason that pivot scale?
So it's not quite standard. I would say if there's one choice that is more standard than others, it's KP equals 0.05 inverse megaparsecs. And changing it actually doesn't change NS. Right? It's only AS that's dependent on the choice of the pivot scale. And then you had your hand up.
So naively, we think that we measure low C, like for this is by using 1.5, like the measurements.
Well, this has, in some sense, this has nothing to do with measurements. In that I'm just telling you about a model, and so I don't want to confuse. So in your model, if depending on what the value of h squared is, and h naught, what is the expansion rate today? That tells you the critical density today. We're not even assuming that here. This is at this moment, and this is saying that there's no assumption here about flatness. There's just an assumption that we have something we could call an expansion rate today.
So basically, we define it.
Yeah, this is a definition of the critical density today. Okay, thank you. Okay, still have a few more key parameters, and let's see. I can lift this up some. And go to some of the neutrino masses is phenomenologically important. They're part of the LambdaCDM model. They're not an extension. Well, I don't know. To me, they're part of the LambdaCDM model, and treated is not standardized. How they're treated is not standardized, and I'll return to neutrino masses shortly, but this is a key parameter, and we'll talk about how they influence cosmological observables. Another parameter. Can you say that again? So this is, we're assuming there's 3 flavors of neutrinos, and this is the 3 mass eigenstates. We have a parameter called tau that, in principle, we wouldn't have to create a new parameter for it. We could calculate it. This is the optical depth to photon scattering off electrons in the reionized intergalactic medium. And let me just write that all out. Intergalactic medium. This is unlike any of the other parameters. In principle, we could calculate it. We specified enough that we could calculate the formation of stars and the formation of black holes and calculate the radiation that's emitted by these objects, the ionizing radiation. We could figure out when the universe reionizes, the history of the ionization fraction, and actually calculate this. So that's in principle, but in practice we can't. It's too hard. And so we have to parameterize it. So this is just one parameter capturing the impact of a whole bunch of physics that's really complicated. We need it. I mean, there's all kinds of things that are hard to calculate in this model, right? Like how many people are going to show up at TASI today. But we can't use a standard model to calculate that. But we don't care about that for standard model predictions because the observables that we can otherwise calculate well don't depend on it. CMB, temperature, and polarization anisotropy are, however, very significantly affected by the value of tau, and so we need to include it in our model as a free parameter. And how do we calculate it? It's the integral from some time, say at the beginning of this reionization process, right? So the universe, there's this ionized plasma. It becomes, the universe cools enough, it becomes this neutral gas, or largely neutral gas, very small density of free electrons around. And then we have stars and quasars forming, and the universe reionizes somewhere around a redshift of 7. And one could calculate it in a given model. One way to think about tau is you're just counting the number of mean free paths that you've traversed. So this is a mean free path to Thomson scattering. And explicitly, that mean free path, this is the number density of electrons, mean number density of electrons. We're talking about the mean value of tau. And what is it telling you about scattering? So if you traverse from T reionization to T naught, the probability of scattering equals 1 minus e to the minus tau, which is approximately tau for tau much less than 1. Which is the regime we're in, basically. Tau is around 0.05, 0.06. That's the optical depth, an important parameter of this model. And then there's the fraction of baryonic mass in helium. The primordial fraction of baryonic mass in helium. Astronomers use Y for this quantity, and we're talking about the primordial value. This is a prediction of LambdaCDM, what this is, a prediction that depends on the baryon density. Or more directly, that baryon to photon ratio during BBN, right? Omega, this little lowercase omega b, that's telling us the baryon to photon ratio today. We can use that to work out what the baryon to photon ratio was during BBN, and that has an influence on the production of helium. So this we get, how is this typically specified? Not all of these things that I've listed, such as the helium fraction, do we treat as free parameters. You might not be able to see this. Let me indent this a little further. What? Was it okay? Well, you're not quite at the end. Well, independent. This always happens. I usually sit near the front row, and the speaker says, "Can you hear me?" I almost always say yes, and then I realize, oh. I was probably not the target audience for that question. Independent sets of parameters. I mean, some of this stuff, right, I'm trying to get you to where you can, start to have ideas about departures, how they affect observables, and that can really be helped by having some basic things that are assumed in a lot of the literature spelled out for you. And so I hope that this is not, that's my purpose for kind of going into some pedantic details here. But there's different ways that people specify the parameter space of this model. Here's one way. So these are these are the densities of the matter components that are free in the model, and then optical depth, and then these perturbation parameters. Now, so this is, I'll say something about neutrino mass, except for that, this is a complete parameterization of the LambdaCDM model. There's nothing said here about the photon density or the neutrino density. The photon density, basically, we treat T naught typically as some absolutely known parameter, and so the photon density is not a free parameter. And then some of the basic assumptions about the early universe then also tell us what the neutrino density will be. So those are huge contributors, over epochs that are observationally important, the neutrino density and the photon density, but they're not free parameters of the model. Another way this gets written down is swapping this for H naught, so it's all these plus H naught. This is probably the most common. Sometimes this AS gets swapped for sigma 8, which is a measure of the amplitude of matter perturbations today in linear perturbation theory. Well, I'll define that later. Okay, but neutrino mass, what do people do about this? So a common choice is to set sum over m nu equals 0.058 eV, and to fix this. So treat it as a fixed parameter. This is the choice in the Planck parameters papers. And why this value? This value makes sense because, so this 0.058 eV comes from delta m squared from solar neutrino oscillations. So we know this is non-zero. And we have delta m squared from atmospheric neutrino oscillations. And you can't, so this is greater than 0. This is greater than 0. You can't get a non-zero mass sum if you have mass differences, and on positive quantities, sorry, mass squared differences, right? And assuming the masses are positive, and so if you take these values, you assume that the lightest mass eigenstate is 0, has 0 mass, then you get 0.058 eV as the lowest mass sum that you can have, and if you have the normal ordering of the neutrino masses. So that's a choice made in the Planck data, then the LambdaCDM model. You have this. Other choices made in the literature is that is basically to place a prior. There's a prior that sum over m nu is greater than 0. So to include it as a free parameter, which very much, sorry, not greater than 0, greater than this minimal value, 0.058 eV. There's an interesting recent analysis where the sum of the neutrino masses is effectively allowed to be negative. So, this is not a physical model, but the impact that neutrino mass has on observables, you can then say, okay, well, what if we had something that had the opposite impact on observables, and we call that negative neutrino mass, and so you can extend that to negative neutrino mass values, and the reason they're doing that is that if you take the data that's most informative on this parameter right now, the best fit value of the sum of the neutrino masses is minus 160 millielectron volts. And this minimal value is disfavored at the 3 sigma level. So it's an interesting thing right now in cosmology, what is going on with our inferences of neutrino mass. yes.
I was just wondering, so what type of priority is set? So this you say above 0.058, but like, what's the range that you consider?
Right. So I'm sure people do different things. So there may be, but usually when people are doing this, they're working with data that is the kind of the most, as far as that upper limit goes, it's the most informative data that there is on this parameter. So it doesn't matter much. The question was, what is the upper, so this is just places a lower bound. For this prior, what's the upper bound? And it's set somewhere where it just doesn't matter because the data are very informative on the upper bound. Yes, you and then you.
Since the optical depth, of course, roughly you said like 7 in a redshift. So it means that like we expect to have like more precision to figure out what is that value, like that we can get these zeros better than the other.
Oh, right. So there are other ways. So the question was, since this tau, the optical depth, all arises at z less than 7, then we must have other ways of probing that. Is that?
Yeah. So for example, here we expect in our combination like 1,000 redshift. Like it seems like it's very long to go.
Yeah.
So it means that we should have like a better resolution for this value.
Oh, well, the difference is that from redshift 1,000, we've got all these photons coming to us, conveying this all, tons of information. So it doesn't matter that it's far away and long ago. We have tons of information coming to us from there, right? So we actually know a lot more about how the universe recombined than how it reionized. So, which may be surprising. You think, usually things that are further away are harder, but the physics is much easier back then. So yes, reionization happened much earlier, but the amount of data that we have on, but basically just how complicated the physics is at that time makes it harder.
And the other question we have is, when we look at perturbations, we assume that there are adiabatic perturbations. Is there any way to prove whether this is true or not?
Oh, absolutely. So the question is there any way to prove whether the initial perturbations are adiabatic or not? So pure isocurvature models make wildly different predictions for the CMB temperature power spectrum, for example. And for example, the peaks are shifted, phase shifted by 90 degrees, and the amplitude of power on large scales is very different. And so that model's been ruled out. Yes. There may be subdominant, you can never rule out that there's some admixture of isocurvature of some kind, but yeah, the data strongly supports adiabatic perturbations as the dominant perturbation mechanism. And they're adiabatic initially, right? We're talking about the initial perturbations. The dynamics then move us away from this delta nx over nx equals delta ny over ny. And you had a question.
Oh, so yeah, my question was, how does the experiment tell the difference between a positive and negative mass?
The question is, what is the observational signature of a negative neutrino mass or a positive neutrino mass? And so for reasons I hope to explain later, the positive neutrino masses, they end up suppressing power on certain length scales, but below below their free streaming length scale, they can't cluster on those scales. They end up suppressing fluctuation power, matter fluctuation power. And so that is the signature that's being picked up on in this analysis. And what does negative neutrino mass do? It's a proxy for something that enhances fluctuation power on those scales, right? So there are physical models that would enhance fluctuation power on those scales, and you can just, so this, how would you get this situation? Oh, I didn't write it down. How would you get the situation where the analysis in this context gives you somewhere MNU equals minus 160 millielectron volts? Well, you're using the wrong model to analyze the data. And if you're using the right model, you'd find confirmation that there is this excess power caused by whatever physical mechanism is doing that in your model. Did that answer your?
Yeah.
Okay. All right. Okay.
If you let the neutrino masses go negative, does this shift your inference for sigma 8?
Absolutely. Yeah. Yeah.
Full direction or?
Oh, yeah. Thank you. So, if you let the neutrino masses go negative, does that influence does that change your inference, or your prediction of sigma 8? So sigma 8, as I said, was this measure of the perturbation amplitude today. It's people in cosmology talk about the sigma 8 tension, meaning that the LambdaCDM predictions given our most informative data, like from the Planck satellite, those predictions are for a particular value of sigma 8, and then you go out and you do measurements that are more directly sensitive to the amplitude of structure formation today, amplitude of structure today, and you generally find a somewhat lower value of sigma 8, and this is at the 2, 2.5, maybe 3 sigma level of discrepancy, so if you are just boosting power uniformly on scales smaller than the neutrino free streaming length, you are going to be boosting sigma 8 and making that worse. Yeah. So there is a range of scales where you could influence this crazy minus 160 MeV result that I did not write down here, and not change sigma 8. But that's something that's an excellent question. That is something to keep in mind. I don't know that it's not clear to me that sigma 8 is a problem for LambdaCDM, but naively, doing this, boosting all length scales below the neutrino free streaming length would make this even worse. Okay, thank you. All right, so. All right, so I think that's good for just covering, kind of, in some ways, putting this all together. I guess I can erase this stuff, and going through key epochs in this model. Key epochs in the LambdaCDM model. Well, first, we've got to start off with, there's something really important that happens that we don't understand at all, right? There's a universe. And so, anyway, I'm also including things, here that are context for LambdaCDM. We don't know that there was inflation. I don't know that there was inflation. But there had to be something that created these initial perturbations, or there's something mysterious about how a universe comes into being that just comes with these perturbations. I don't know. This is a mystery where these perturbations come from. Inflation is it is a remarkably beautiful theory in many ways, and it raises a whole lot of questions. Then inflation ends, right? We know that that has to happen if we have inflation, inflation dilutes everything. It's this expansion that is diluting everything else. You get this zero temperature universe. And when inflation ends, you have to somehow map that onto the hot Big Bang. We need to reheat. So this energy in the inflaton field has to somehow convert into its thermal population of the particles of the standard model, and particles and fields. And then we need, the baryon to photon ratio is small, but it's not zero. We need some way of creating that excess of baryons over antibaryons, leptons over antileptons. So these aren't things described by the LambdaCDM model, but they're things that must have happened. to get us onto what is described in the LambdaCDM model. And now, with this happening, we know we have various standard model, particle physics standard model degrees of freedom with thermal distributions. So we've got black body distributions in top quarks and bottom quarks, et cetera, right? All the neutrinos, gauge particles. When their mass is less than the temperature, right? Their rest mass energy is much less than their, the mass is less than the temperature. And when their mass starts to become comparable to the temperature, which happens, of course, for different particles at different times, you have this dumping of their entropy into the rest of the plasma. As for any particle x. We have the quark hadron transition happens, and we lose more degrees of freedom. Why do we care about degrees of freedom? Why am I even bringing them up? I mean, how are they relevant dynamically? So, and for a distribution of bosons, with zero chemical potential in thermal equilibrium, this is baryon. For this boson, sorry, this looks like baryon. Right? We have this, and then we have basically the same expression for fermions, difference by a factor of 7/8. And this G is counting the number of degrees of freedom, right? This is flowing from, I wrote down a phase-space distribution function for bosons earlier, and if you integrate over all the momentum states, and you count the energy of each particle, right? You get this result, and it depends critically on the degrees of freedom. So with the photons, you have the two spins, you have the two spin states, and so this is 2. But for all the other particles you're adding to the density, right? So you have these thermal distributions, you're increasing the density, and that necessarily ends up increasing the expansion rate. So this temperature expansion rate relation depends on the degrees of freedom, and they become, at sufficiently early times, this is in the hundreds, right? 100 and something in the standard model of particle physics, in the standard model of cosmology. So that's important. And it's important in terms of, there are particle physics processes, looking beyond LambdaCDM, beyond the standard model of particle physics. One of the key contributions of cosmology to particle physics model building is constraints on light relics that might have been created in this plasma. And understanding their influence on the light relic density today depends on when they froze out and the history of these degrees of freedom over time. Quark to hadron, more degrees of freedom lost as the quarks become bound in protons and neutrons. Helium forms in BBN. At about 0.02 mega electron volts. And good. as I said, we have this, or as one of you said, and I repeated, ionized plasma goes to a neutral gas at Z is approximately 10 to the third. And for tau equals 0.06, 94% of the CMB photons that we observed today, this is when they last interacted with matter. Right? So that's an important epoch. And then neutrinos become non-relativistic. At least if the straightforward interpretation of the atmospheric neutrinos is that at least one neutrino has a mass of 0.05 eV or more. Does anybody have a guess at what redshift that starts to become non-relativistic? Maybe not this close to lunchtime. Okay, good. Then I feel better about telling you. So they become non-relativistic at Z greater than 250. At least a a 0.05 EV mass neutrino would become relativistic at Z equals 250. A redshift of Z equals 250. So for much of the expansion of the universe and through this growth of structure, the neutrinos are, at least one species of neutrino is non-relativistic.
You're going to talk about these, that decoupling, of course.
Sorry?
That
Decoupling
decoupling.
of the oh, so, yeah, let's see. I missed something that I really, I skipped a couple things I wanted to include. And is that clock in the back? The back clock is a little fast.
3 minutes about.
Okay, thanks. So we after this, so I'm just going to say, after the quark hadron transition, weak interactions freeze out. So those interactions that convert protons and neutrons, they stop being effective at changing NP over N gamma. NP over NN, right? The number density, the ratio of protons to neutrons. That's really important for how nucleosynthesis proceeds. Also important for nucleosynthesis proceeds, and the density of neutrinos relative to photons. We have E plus, E minus undergoing this transition, right? That so many particles do, where they become non-relativistic, and instead of having this like black body radiation in electrons and positrons, it all gets dumped into the plasma, all except for that tiny excess of electrons over positrons that's there in the lepton asymmetry. So we have E plus, E minus going almost entirely to photons, and a tiny bit goes to neutrinos, because this is only very soon after this the weak interactions decouple. So that happens, and it really boosts the photon temperature relative to the neutrino temperature. The neutrino temperature today is just a little below 2 degrees Kelvin, and while the photon temperature is at 2.73 Kelvin. So they become non-relativistic. We have the first stars. Maybe at Z of around 20. Neutral hydrogen, as I said, neutral hydrogen goes to ionized in the IgM. And again, that's at Z of approximately 7. And then we have TASI 2024. Okay. All right. So that's, anyway, I think this is a good place to stop. But I guess we have time for one question, or until we're cut off. Anyway, thanks for all your questions during. Yes?
You mentioned zero chemical potential for the photons. Is that something that we measure? Is it an assumption? Is it something that if you modify, how would it change the results for time?
So we have so the question was that I mentioned zero chemical potential for the photons. Is that something that's been measured? Is that an assumption? And it's something that we completely expect in this standard model. It's also something that we have very tight upper limits on from measurements of the spectrum of the CMB today, right? So how the intensity of the CMB changes with photon frequency. And that is, we have not detected any departure from a black body, and there's some very, very precise measurements, and there's particular limits on the chemical potential. Actually, I take it back about it being zero in the LambdaCDM model. There actually are standard model processes that change that away from zero at a very small level, and that we might be able to measure someday. There's also exotic processes that are constrained by, another thing I failed to write down. There's a key epoch where at about z of 10 to the 7, which is after BBN, processes standard model processes that change photon number densities. So interactions where you create more photons or destroy photons, those become ineffective at about z of 10 to the 7. What that means is that energy that you inject into photons after then, you can't change the number. You can redistribute that across momentum space, but you can't change the number of photons. And so you can't get to a black body distribution. You'll have a non-zero chemical potential. So the upper limits on the chemical potential constrain exotic processes that dump energy into the plasma at z less than 10 to the 7. Okay, and I think we're done.
We have a lot of questions. Let's stop here. Let's thank Lloyd.
Thank you.